Hello student, to the Foundation of Classical Electrodynamics course. Under module 4, today we have lecture 66 and we will going to continue the discussion on the Maxwell's equation that we started in the last class. So, today we have class number 66. So, what we have in the last class, let me make a small recap here, that we wrote the 4 Maxwell's equation in this way. Divergence of E is equal to rho, which should be a function of r and t divided by epsilon 0. This is equation 1. Equation 2 is divergence of B equal to 0. Equation 3 was curl of E plus del B del T, that was 0. And finally, equation 4 was curl of B minus mu 0 epsilon 0 del E del T is equal to mu naught J as a function of r and t. That was 4 equation, but we had a set of equation which is homogeneous. These 2 equation was homogeneous, equation 2 and 4, because right hand side there was no source term. So, these 2 equation was homogeneous. And rest of the 2 equation, here we had the source term, this one and this one, we had the source term sitting here. One is rho and another is j. So, these are 2 source term that is there. So, we extract the information of equation 2 and 3 and we eventually have this equation. So, what we get from equation, the 2 homogeneous equation 2 and 3, we had this, we had B is equal to curl of A and E is equal to minus of gradient of phi minus del A del T. This we get. So, we extract the information of equation 2 and 3 and eventually get B and E. Now, you can see that B and E is having the 6 component and this 6 component can be extracted from the 4 component of A and phi. So, I should make a note here, the set E and B, which eventually try to solve these 2 vectors, they are having 6 components and this information I extracted in terms of A and phi. Now, phi is a scalar quantity that makes the total number of component 4. So, we now have 4 component. So, all the information that we had here we can we can have the E and B, the 6 component, from this information of the 4 components. So, we can reduce the number of components. Now, the next thing is how to solve A and phi. Should we have equation for A and phi? And in order to do that, last day we mentioned that we will put this information B is equal to curl of A and E equal to minus of gradient of phi minus del A del T into these non-homogeneous equation, that is in equation 1 and 4. So, next step is this. Now, let us plug the equation of E and B, these two equations we are having right now in terms of A and phi, E and B in other two which is equation 1 and equation 4. Two equations, they are non-homogeneous equations. So, let me first write down this first non-homogeneous equation. So, this is divergence of E was equal to rho function of r t, this function of space and time, and epsilon 0. Now, I put E in this equation, I put E is equal to minus of grad phi minus del A del T. So, if I put there, then I simply have divergence of minus of grad phi minus of del A del T is equal to rho, which is a function of r and t divided by epsilon naught. So, this thing is simply minus of Laplacian of phi minus del A del T, then divergence of A. I just put this divergence inside the operator del A del T, and then in the right hand side I should have rho divided by epsilon 0, rho being a function of position and time. That is one equation we are having, that is all. Okay. So, let me, so this is say equation 5. What is the other equation that I like to exploit here? The other equation is this one. So, we had curl of B minus equation 4, fourth Maxwell's equation, del E del T, that is equal to mu 0 J R and T. Now, you know the B, because B is curl of A. So, I put here again B is equal to curl of A, and not only that, I need to put E also here, because E is there. E is equal to minus of grad phi minus del A del T. These two I put here in this equation, and let us see what we get. So, we get something like curl of B. So, we should get like this, curl of A, I just replace B to curl of A, minus mu 0 epsilon 0, and then I have del T of this quantity. So, here we had a minus, I can put it as plus, and then it should be divergence, it should be gradient of phi plus del A del t, and that is equal to the source term mu 0 j r t. We get this. Okay. So, this term, if I want to simplify, then we know the famous identity, it should be Laplacian A, then minus of, sorry, then plus gradient of divergence of A, and then we have 1 by, so 1 by mu 0 epsilon 0 I now write like 1 by c square, because we will see later that c, which is the velocity of light, can be represented in terms of mu 0 and epsilon 0 in this way. So, let us write in this way only. We will going to discuss this part again in next class maybe. And then we have del t of gradient of phi, and then we have plus 1 by c square, then d 2 a d t square is equal to mu naught j function of r and t, that we get. Okay. So, we have a very equation where many terms are there, but anyway. So, let us combine few terms here and let us do in this way. Let us write this equation like gradient of, because we have two gradients. So, gradient of, let us make like divergence of A, and then plus 1 by c square, then we have del phi del t. I just extract the gradient out of this. This is one equation, one part of this. So, I write this part, and another part is like 1 by c square d 2 a dt square and minus of Laplacian A, that is mu naught j r t. Okay. So, these are the two equations. So, I can't do much after that. So, we need to put certain condition here. So, that we are going to discuss. So, this is say equation 6. So, let me jot down what we get so far. So far we have what we have? We have one equation which is grad square phi plus del t, then divergence of A, that is equal to how much? That is equal to minus of, because I take the negative sign, this negative sign I take. So, it should be minus of rho is a function of r and t divided by epsilon naught. That is one equation I get as equation 5, and equation 6 what I get is this one. If we write side by side, then we will find something, that divergence of gradient of A and then 1 by c square, I have del phi. So, I have del phi del t, and then minus of Laplacian of A minus 1 by c square, and then d2 A dt square, that is equal to mu naught j as a function of r and t. So, these two equation we have. Now, after that we need to put something to make this equation little bit simpler, and the way we do is called the gauge. So, now here we will do something called gauge invariance. The idea of the gauge is not new because we have already introduced that in earlier class. So, we will exploit this once again. What do you mean by gauge invariance here? What do we mean? So, B is equal to curl of A, and we find that this A is not unique. So, it is not unique. So, we can choose as per our convenience, and we, for example, I can have A prime which is the given A plus the gradient of another function which may be a scalar function time, which may be a function of space and time, and that eventually gives the same B. It leads to the same B. That means, if I do curl of A prime, I will return back whatever the B is there, that is 1. So, I can manipulate my A through this function xi, right. So, I have a liberty to take my A. Now, not only that, I can also have liberty to have the phi, this is a vector potential. So, the scalar potential phi prime I can write in this way, whatever the phi is given, and minus, if I do this quantity, if I do this thing, then A and the set A prime and phi prime will going to produce the same B and same E. Let us check that first, whether they are producing the same B or same B we know that, but same E, whether they will going to produce or not, let us check. So, first, so I am saying that A phi, the set, and A prime phi prime produce the same B and E. So, let us check that. So, if I make curl of A, so that we already did earlier. So, let me so if I make curl of A prime, it should be curl of A plus gradient of this, and that is eventually curl of A plus 0, because gradient of something, if I took a curl over that, it should be 0, and that is nothing but my B. Okay, so, A prime is producing the old B. What about the E? Because E is, so if I want to find out this quantity, phi prime minus del t a prime. So, this ideally should give us the same E. So, let us check whether it is giving the same E or not. So, I have this, and then it should phi prime is my phi minus that quantity. So, it should be phi minus del t and minus of del t a prime is a plus of this. So, what I am getting here, minus of this plus of, let us put this inside. So, I have now gradient of chi, then minus of del a del t, and then minus of d dt of this quantity. Note that these will going to cancel out, this quantity and this quantity will going to cancel out, and eventually what I left with is this minus del a del t, which is equivalent to my old E. Okay. So, that means A prime and phi prime will produce the same E and B. So, I have, but I can manipulate my A prime and B prime. So, that means the outcome is we are giving a freedom to choose A and phi such that the equations become simpler. That is the goal. So, whatever the equation we had here, so these two equation written here, these two equation, this one and this one, I need to in fact solve to find out A and phi, and once we solve for A and phi, then I can use these two equation again to find out my E and B. That is the strategy. But in order to solve these two equation, we need to, this is not very easy to solve, but we can make some mechanism through which we can make this equation simpler, and this mechanism is basically the gauge invariance. So, I can choose my A and phi suitably to make these two equations simpler. Now, the question is how to make this equation simpler. So, one way is the Coulomb gauge that we discussed earlier, and the Coulomb gauge is suggesting that is the condition of the Coulomb gauge. So, first we will discuss about the Coulomb gauge. And this Coulomb gauge is suggesting that this is, we put a constant. A constant is that my A should be such that I can take my A in such a way that the divergence of A should be 0. Now, the question is, suppose A is given to me, suppose we have a suppose we have a such that the divergence of A is not equal to 0, but we know the value and this is not equal to 0. And if this is not equal to 0, then we say this value is say some scalar field f r t. Now, we can always make a prime such that in this way I can make a prime plus so this is the strategy, because I can have my A in this way. So, now I make a divergence both the side of this. I can always have, so let me write it here. I can always have my A prime as A plus this will produce, because this will produce the same B. Now, I put a divergence over this A prime. When you put the divergence over this A prime, then divergence of A, already if it is given, so I put this A, and divergence of the gradient of chi is simply Laplacian grad square chi. So, now we demand, now we set that this quantity must be 0. We set that. So, that is our Coulomb gauge condition, right. Our Coulomb gauge condition is the divergence of A has to be 0. So, that we set. If we set that, then I can have an equation, then the chi has to satisfy this equation. Then the chi has to satisfy a equation like this, and I have a freedom to choose my chi. Mind it, chi is in, this is my hand. So, we can choose my scalar field chi, which we call the gauge function, such that it is a solution of the equation, it is a solution of the equation this. Which equation? It is a solution of the equation, this equation. This equation, and we know that this is what is this equation? This is Poisson equation, and we know that how to solve this. This is our Poisson equation. So, that means under Coulomb gauge I can always make, I can choose a prime in such a way that I can always have the divergence 0, and this is the recipe to make this to get this divergence of A equal to 0, because I have a function chi which satisfy the Poisson equation and that. Now, the question is what should we get after making that, because these two equation, if you now see carefully these two equation. So, under Coulomb gauge, this term will going to vanish, and if this term vanishes, then phi should have a relatively simpler equation. We should have a relatively simpler equation for phi. That is the advantage we are getting, and that phi if I put in the next equation, we should get a solution. So, let us do that part as well. So, under Coulomb gauge, so whatever the equation we had, say let me put a name here, this equation, say equation, already I had this name. So, equation 5 I think, yeah, equation 5 and 6. So, this is equation 5 and this is equation 6. I rewrite that again here. So, equation 5 becomes, under Coulomb gauge, equation 5 becomes this, grad square phi is equal to minus of rho by epsilon naught r t. What was equation 5? So, equation 5 is this. Better I should write equation 5 because I need to go up every time. So, better I just, so equation 5 becomes, so let me write equation 5. So, what is equation 5? Equation 5 was this, gradient of phi and then I guess plus del t and then divergence of A, and then I have equal to minus of rho by epsilon naught. Rho should be function of r and t like this. So, that was my equation 5, and under Coulomb gauge means I should put these equal to 0, that is the condition of the Coulomb gauge. So, this equation 5 becomes this. So, now this is a Poisson equation again, and in principle we have a solution for the Poisson equation. So, I can readily have my phi. So, what is the strategy step by step? Let me go back. I had this equation 5 and for which maybe my gauge condition gradient divergence of A is not fulfilled, but I have a liberty to choose another A prime such that this A prime can satisfy that, and I can have an equation for Coulomb gauge. This is the condition I need to satisfy, but even if this condition is not satisfied, I can have a recipe to make another A prime here which can satisfy the Coulomb gauge, and for that I need to choose a function chi, a scalar field, which is again following this Poisson equation, where if it is not satisfying, so this value is given and I am going to exploit this value here to find out my chi and put it back there to find A prime. Now, Coulomb gauge is satisfied, and if the Coulomb gauge is satisfied, then I can have my equation of the potential phi in a simpler form, and that is my Poisson equation. Okay, that part is done. So, I can modify my equation 5 in this way. What about the 6? Because another equation I need to solve simultaneously. So, let me write down the equation 6. So, what about equation 6? So, what is equation 6? Let me write first. The equation 6 was divergence of int of A plus 1 by c square d phi dt minus of what was that? Let me go up and check. Yeah, minus of A, and this is forming something wave equation. We will come to this part again, because I have already discussed about the wave equation. So, now if you look carefully, this part of the equation, this is nothing but the wave equation. We will discuss later, maybe in the next class. So, that is the equation we had. Now, under Coulomb gauge condition, what we get is this term is 0 here, and that is all. So, if this term is 0, then we have the equation which in this way. So, we eventually have the equation like divergent the gradient of A, I am writing this part, minus of 1 c square d to A dt square, that is there, and in the right hand side I should have say minus of mu 0 j r t, and then I have plus of 1 by c square del t and gradient of phi, that we are having. So, how do I solve that? Would it be possible to solve? Because in this case, okay, I understand this is a Poisson equation and I can solve phi. What about this equation? After Coulomb gauge, I have a little bit simpler form of equation 6, but still this looks very cumbersome, but in principle you can solve it, because this is a source term that should be given, and now this portion is known. Now, this portion is known. This portion is known because you have already solved that. So, you solve that and you know what is my phi. So, phi as a function of r and t is known now, because you know how to solve this Poisson equation, and this value should be known. And now, this known value if you put in the right hand side, so it becomes right hand side is completely known, and you have a wave equation with a source term, and in principle you can solve it, but still there is a cumbersome process to solve this wave equation with a source term. So, maybe we can have a better gauge. So, this is a Coulomb gauge for which you will going to get, and in principle in Coulomb gauge you can simplify the entire equation in this way. You can calculate your phi by Poisson equation, then you put this phi here in this equation 6, and then you figure out, then you solve for A, and now your A and phi is known. Once your A is phi is known, then you can exploit this A and phi to find out your E, which is minus of these minus del A del t minus of the gradient of phi minus del A del t, and your B is curl of A. So, both you can calculate, because now this is known and also A is known. So, in principle you can calculate your E and B. Well, this is the way to solve A and B by using this gauge thing. In the next class, today I do not have time, in the next class we will discuss another gauge which is called the Lorentz gauge, and in Lorentz gauge you find that the expression become a little bit simpler and it will be much useful. So, with this note I would like to conclude here. Thank you very much for your attention, and see you in the next class.